Okay, welcome to day 2 of HoTT-UF workshop. And our first speaker today is Nima Rasekh from EPFL, and he will talk about a step towards non-presentable models of homotopy type theory. Nima, the stage and the moment are all yours.
Okay, thanks, Chris. Thanks to the organizers for making this happen. I'm not really a type theorist by heart. I'm more of a homotopy theorist / higher category theorist. So it's always exciting to be in like type theory events and like learn from your perspective. So, okay. So let me just give you like a kind of like a very broad, very subjective overview of what MATNAF is about, right? So on the one side, there's syntax and there's semantics, and then both of them kind of in my mind break down to like homotopical versions versus non-homotopical versions. And while I was doing this talk, I realized I'm not really a big fan of slide talks, like not necessarily listening to them, but making slide talks. So in order to like spice things up, I decided to like color everything. And so this color scheme will kind of persist throughout the talk. So if you get bored by what I'm talking about, maybe you can figure out how the coloring works. So maybe that's like a nice challenge. So the goal is kind of to compare the semantics and syntax sides of stuff, right? To like see how they compare and how you can translate between them. So first, let's see what has been done. So there's this one story between extensional type theories and one category theory. So I'm not going to explain this whole diagram because it's kind of large, but the point is there's this really nice translation between various type theories with more and more constructors and various kind of categories with different universal properties. And so if you want to kind of see a nice overview of the history of it, you can check out like the book by Lambeck and Scott, which kind of goes into the details of who contributed and how many, in which ways. But the thing we want to focus on is the infinity version of this. So like intentional type theories versus infinity categories. And here things are much more spotty, right? So lots of things have not been done yet. So there's this one nice result due to Kapulka and Shumilo that compare type theories with dependent sums with finitely complete infinity categories. So this is, I would say, still reasonably new. It was published last year. There is also like another paper by Kapulka that takes intentional type theories with pi types and gives a local Cartesian closed infinity category. And so this also kind of uses the same kind of machinery of vibration categories introduced by Shumilo. But again, there's kind of like no way back for now, at least. And for the last like row, it's even worse than that. We don't even like we don't know how to like make infinity categories out of homotopy type theories, and we don't even know what kind of infinity categories we necessarily get. So like the target is open and the way to get there is open. Very, very open. There's a little bit we can say about going back. Namely, there's this magical word called presentability. So if you start with a presentable locally Cartesian closed infinity category or a Grothendieck infinity topos, which is kind of presentable infinity topos, then we can go back, and that bunch of people have contributed to that. So it's basically the Grothendieck infinity topos work is recent work by Schumann, who introduced this notion of a type theoretic model topos. So if you fill this into this diagram, it will look more like this. So if presentable or if Grothendieck, we kind of can go from the semantic side back to the syntax side, but not in general, right? So there's still it's not a clear way of how to start with an arbitrary infinity category and go back to like these type theories. And so we still don't know really for sure what fits into this question mark in the bottom right corner. But if you just want to follow the logic, the word that should fit here is some sort of elementary infinity one topos, right? So this is kind of the consistent thing. Which into this, all these third diagrams, what they suggest is we should care about what elementary infinity one topos is, develop it, and then try to prove a result that kind of is analogous to the relation between extensional type theory and elementary to one topos theory. But turns out studying elementary one topo is really hard. There's a bunch of stuff I have done in this direction. There's a bunch of things that other people have thought about, but I would say it's still work in progress. And in particular, nobody knows how to strictify an arbitrary infinity category that is not presentable. So I guess this will take some time. Like we will have to wait a couple more years to get this done. So let's have a more modest goal. Start with like try to constructing specific elementary infinity topoi, and then try to relate it to homotype theory. And so this is the step, right? The title, there's this word, a step towards. So the step is trying to like construct new elementary infinity topoi. So how can we do that, right? And so now I want to move on to a definition of elementary infinity topos. And here I have to give the warning. the definition of elementary infinity topos is a little bit of a chicken and egg problem. But whatever definition you propose, you can't know if it's correct unless you already have some relation to homotype theory. But then if you don't propose a definition, you can't even compare. So whatever definition is given might be updated depending on future results. But I will work with some definition. And so I'm just giving you an idea that things might change in the future years based on new events and new results. So having said that, so here's the definition that I'm just going to use for this talk. The first three conditions are more or less like not controversial. They're already satisfied by elementary 1 topos. The controversial one is the last one, the one that people debate about. So what I'm saying, the last one I'm saying is I'm taking this over category functor. So what is it? This equivalence symbol means like the space of maps over some object is covered by certain representable functors. So let me explain what this last one means so that you get like a better idea. So first of all, I'm saying there's a map. Exists some kind of map here. This means there's a universal fibration over U. So U is the universe, has a universal fibration, which is just the image of the identity. But I'm not just saying there's a map, I'm saying there's an embedding. And the embedding means it's univalent. So that's just like one of those ways of characterizing the univalence axiom in an infinity category. It's exactly saying the embedding this map here from the representable functor is an embedding of like functors. And finally, I'm saying this map is jointly surjective, which means every map is classified by something. And so if you put all of these three together, 1, 2, and 3, they're just saying there are enough univalent universes, right? So this is kind of the analogous kind of hot usage of the universe, a univalence axiom, I guess. The exact characterization of universes is still up to debate, specifically how strict you want their existence to be and how strict their relation to each other is, and what you kind of need to define them functors. So this is not necessarily a final definition. And in particular, what we very often want is we want these universes to be closed under limits, co-limits, pi types, and so on. For the purpose of this talk, I'm not going to make any of these assumptions because they don't really matter. If you don't like this, just assume your universe is closed under whatever you like it to be closed, and just keep it for the rest of this talk, and it will work. Like it doesn't really matter. For this talk, just take your universe to be what you want it to be, and just keep it consistent throughout the talk. Okay, so let's do a sanity check. I gave a definition of an elementary infinity 1 topos. It should relate to some other previous stuff. So here's like an easy observation. If you take an elementary infinity 1 topos and look at the 0 types or 0 truncated objects, you just get an elementary 1 topos. So it goes back to like classical definitions. And if you add a presentability condition, you get exactly a Grothendieck infinity 1 topos. So it's like a common generalization of two already known subjects, and that's the good, right? That means it at least fits well with established definitions that we already like. And so in particular, what this means, if you combine this, so if you combine number 2 and the result by Schumann, this implies that a presentable elementary infinity 1 topos is already a model for HoTT. It's like it already can be represented by a type theoretic model topos, and then the all results follow. So the question that remains then is, can we construct non-presentable elementary infinity 1 topos and then prove that these are also models for HoTT? And so for the rest of the talk is to focus on well, the first part, construction. So how can we do that? How can we construct non-presentable ones? And for this, we go back to like the bag of tricks of elementary topos theorists and look at this thing called filter construction. So what is a filter? Let's fix a finitely complete 1 category. So let's go back to 1 category theory for now. And that's F is a filter. It's a subset of the subobjects of the final object. So 1 here is the final object. And just take a subset of that has these 3 properties. It's non-empty, which is actually equivalent to just having the top subobject. It's closed under intersections, and it's closed as upwards closed. And the goal is to define a new category E sub F. So how do I define this new category? The objects are exactly the same, easy. For the morphisms, I take partial maps, so maps that are defined with domain x times u. And then I'm identifying them if they're eventually equal, right? So if 2 maps, 2 partial maps are equal, if they exist like a smaller kind of smaller subterminal object where they then happen to agree. And this is a equivalence relation, and then with this equivalence relation, I get like this nice Hom set. And the key result about those, which is like you can just prove yourself, it's like not that hard, but you can also find in sketches of an elephant, for example. If E, like E as a category, has, let's say, finite limits, or has a local Cartesian closed structure, or has a sub-object classifier, then the natural quotient map will preserve this structure. So if, in particular, if E, the E you start with is an elementary 1 topos, then EF is 1 as well. So it will preserve the classical kind of topotheoretic structures. That's nice. So now we want to infinitize it, right? That's the dream. And in order to infinitize it, we will actually have to, like, this is one of the very few occasions, maybe in your, like, all of your life, and when you go to an infinity category talk, and where actually models will come up. So there you go. I will actually give 2 constructions, and it depends on which model I'm using. So first, for Kahn-enriched categories, and so the reason I'm doing this is because they're different. I mean, they turn out to be equivalent, but they're different constructions for each, and you can pick which one you like more, I guess. So for Kahn-enriched categories, the construction is super easy, right? So if you take a category and it's just enriched over Kahn complexes, then you can just think of it as a simplicial object in categories, where each level is just the nth level of my simplicial set enrichment. And so now just apply it level-wise. Like take your simplicial category, apply to each one of those simplicial levels of the category the filter construction, and then stitch them back together. And to be clear, there's something you have to prove here, obviously. It's not immediately clear that what you get is a Kahn complex and so on, but I just claim you can do it. It's not tricky or hard. As soon as you realize what you want to do, it's a reasonably standard exercise. So you get this simplicial category CF, which is also Kahn-enriched. For quanti-categories or complete sequence spaces, you can't do that because they don't have well-defined meaningful mapping spaces. But you can do like this trick here. What you can do is find this functor, which has an input. Well, so the input is just F, this post at F, and the output is answered cat infinity. And it just takes every object to the over category and every inclusion map from these sub-objects into the product map. And then I just take the co-limit of this inside cat infinity. And so CF is just the co-limit of this functor. And so I just wanted to be clear again, these 2 constructions, if you start with 1 and then change the model and then do the other construction, you will get equivalent things. They're not different in many things. And so the claim is that the same thing holds. If C has any desirable property, such as finite limits or co-limits, local Cartesian closed structure, sub-object classifiers, or universes, then CF has exactly the same property. And so in particular, if C is an elementary infinity 1 topos in the sense I defined, it will have all 4, and then CF has all 4 as well. Nice. So yeah, so here, the next question then is, so what we wanted are non-presentable examples. So does this help us get non-presentable examples? And I claim yes. And here we go back again into the bag of tricks of the classical elementary topos theorists. So there's this new result this is nice result due to Adelman and John Stone from 82, which, and I made it a little bit more specific because I don't want to give the most general form for the purpose of this talk. So here the set is literally the category of sets, and I is some set. And I want to take F, so set to the I is just I indexed sets. And I want to take a non-principal filter on this set to the I, which just turns out to be a non-principal filter on the power set of I. I haven't defined non-principal filter. If you don't know what it is, I will give an example soonish. And then the claim is that in this case, the filter construction on the set to the I is a non-presentable elementary 1 topos. And so then correspondingly, it's also a model for a higher order type theory. So now I will generalize it and claim the same thing holds. It almost similarly, like in the same way, right? Just replace set by Kahn, and now you apply the same non-principal filter, and you get a non-presentable elementary infinity 1 topos. And here's actually like a very concrete example. Take the set I to be n, the natural numbers, and take F to be the Fréchet filter, which is just a filter of cofinite subsets of n. Then the thing you get is Kahn to the n, the filter construction on that is not only not presentable, it doesn't have infinite coproducts except for the initial object, and you can actually prove that the natural number object is not standard. meaning that the standard natural numbers are not a surjective cover. But not jointly surjective. So this is like a very kind of concrete actual example where you can actually see what the objects are, what the morphisms are. So it's reasonably concrete. So before we finish the talk, let's summarize. So what we wanted models for homotype theory. So the assumption of the talk is you like homotopy type theory. You want models. The dream is eventually there will be this nice notion of an elementary infantropos. It will give us all the models. But we're not there yet. So let's start with a little bit more modest. The presentable case is already covered by Schumann. So let's do the non-presentable case. That's too hard. So let's try to do an example. So I gave you an example of a non-presentable elementary infinity 1, 2. The question that remains now, is this a model? Can we prove this is a model for HoTT in some sense of HoTT? And the answer I have to give for now is, I honestly, I don't know. And here's the struggle in some sense. The construction of this infinity category is in a sense a filtered co-limit. That's what it really is. It's a filtered co-limit of infinity categories. And we don't know anything about co-limits of models for HoTT. At least I don't know anything. And I looked in Schumann's paper and there was nothing in there. And I emailed Schumann and asked him and he didn't know either. And so maybe if any of you know, then please let me know. I would love to hear about it. But at least that's kind of like an open question, that if I know that if I have a diagram inside infinity categories and the value of this diagram is itself valued in models of HoTT, in models like in type theoretic model topology or something, what can you say about the co-limit of that? And so with that, if you want to learn more about the details, feel free to check out the paper. It's on the archive. Thank you, and let me know if you have questions.
All right, well, let's thank Nima for this great talk. So please don't unmute your microphone, but let's all clap. I'm just gonna say Nima was very good with time. So we have a lot of time for questions. So if we can do it in a civilized manner, that'd be great. So let's try unmuting your microphones and ask questions. So far, it's very civilized, but that's not what we're going for. Okay, I mean, civilized is what we're going for, but
maybe it's too civilized by now. Like you scared off everybody.
Yeah, scaring people with civilization. Yeah. Okay. Well.
There's someone in the chat who says, "May I ask a question?"
Yeah. There's.
Yeah. Thank you, Nima. Just to present, do you assume initiality in some form when you talk about models or not in this talk?
Do I assume initiality? I honestly don't know. I will assume no, but I don't know.
Okay.
I mean, this is my honest answer. I don't know.
I mean, so there are those results by like some Polish Canadian dude mentioned in the beginning. So these results assume initiality.
No, the thing is, if I understand correctly, Voevodsky just wants to call a model when initiality is given. Otherwise, he wouldn't call it model. So would you call it model?
Well, so
your concept of model.
When you talk about translation from type theories to infinity categories, like they assume that you go from, I mean, it starts with the definition of type theory as an already contextual category, right? So,
if I may add a word on this, I mean, I understand. When I hear Nima's talk, it's not assuming initiality, it's taking models of type theory to be defined as a contextual category with certain extra structure. And then initiality is what would justify that terminology as a good terminology. But this holds without assuming initiality with that terminology defined that way. That model of homotopy type theory, meaning a contextual category with a certain extra structure. And then if initiality holds, you also get the translation from syntax. But either way, these results don't rely on that.
Oh, okay, thank you.
No, but the phrasing is from type theories to infinity categories, right? And so you take type theories to mean contextual categories. At least the way these results are made precise. And
yes,
that
that's
assumes,
exactly what I had in mind. Yes, exactly.
Okay, I think there was a question in the chat whether someone may ask a question, which is one of the.
Yes, so please, can I go ahead? Excuse me for my question. It will seem quite naive, but I don't have much knowledge of infinity topos. So I wanted to know if the sub-object classifier in this case isn't supposed to come up with more structure than just a Heyting algebra. And if this is the case, would it be more relevant to have something else than filters to quotient out from?
So I mean, I feel there are two questions there. So the sub-object classifier probably won't come with any more structure, because I mean it's still only classifying sub-objects, and sub-objects are, even like if you start with an infinity category, the collection of sub-objects of any object is still just a poset. However, I think the other part of the question is kind of interesting, and I agree that what we could ask ourselves is the same way that we start with a filter, like a choice of sub-objects or something, and then apply a construction to get a new infinity category. Then maybe you could start with something more general now that we have infinity category, and like try to like get a new construction, like a more general colimit diagram rather than just like a filter poset. I don't know. I mean, I agree that this is like something that I think should be like might be possible, might make sense, right? So I guess the example we could look at, if I could go back, is so here we take, so here I start with set to the I, and then I apply the filter construction to that by taking a subset of pi. Here I start now with Khan to the I, but I could start with Khan to some Khan complex. I could make sense of that, and then I could ask myself maybe like a more general construction than a filter construction would make sense here. But I don't know. I've not thought about this in too much detail.
Okay, thank you very much.
Okay, I will allow one more short question. If we okay, short to medium length question, let's say. If we have any questions of that length. Oh, wait, one more minute. No, not a whole minute. I'm not going to wait a whole minute. Okay. Well, okay. If I don't see any further questions, I suggest that we thank Nima again for this great talk. So please join me in applauding. All right. Thanks a lot.